Hi, in this video, we'll talk about the paper Information Prioritization to Empowerment in Visual Model-Based Reinforcement Learning. Target the problem setting of learning latent space models for control from visual observations. In complex environments with high-dimensional observations, that is images, modeling the full observation space can present major computational challenges. So we need some mechanism for learning representations that prioritize functionally relevant factors for the current task instead of trying to model the entire observation space. In this paper, we propose an approach that extracts controllable factors from the environment and performs planning to the learned representations through variational empowerment. Controllable representations are features of the observation that correspond to entities which the agent can influence directly through its actions. In the figure on the right, A is the action executed by the agent, and S plus corresponds to the controllable factors of the environment that are influenced by the actions. S tilde minus correspond to factors of the environment which influence the rewards but are not influenced by the agent, and ds minus are things in the environment that correspond to distractors that do not influence the reward and in turn cannot be influenced by the actions. Our key insight is to integrate a term inspired by variational empowerment into a state space model based on mutual information. This term, as we'll show, prioritizes information that is correlated with action, thus ensuring that the functionally relevant factors are captured first. Furthermore, we'll show that the same empowerment term also promotes better exploration during policy learning, especially when the reward signal is not strong enough to drive exploration in the early stages of learning. This brings us to our approach, InfoPower. To obtain a sufficient objective for control, we need to maximize mutual information between latent states and the observations, in addition to abstracting out controllable representations. Following prior work, we avoid a reconstruction objective and instead employ a contrastive learning term. It directly maximizes the mutual information between the observations and the latent representation. This contrastive objective has the positive observation OT times step T and the negative samples O hat T. The negative samples correspond to observations at different time steps and observations in different batches of the buffer. We then have a reward objective that maximizes the mutual information between the learned latent representation and the reward. This is important in order to learn a reward predictor such that the agent can plan using latent representations alone without having access to the corresponding observations. Finally, the empowerment objective, as described before, prioritizes capturing the controllable aspects of the environment in the learned latent states. This prioritizes capturing the functionally relevant factors instead of capturing everything that is correlated with the observation. This term is formalized by the mutual information between the action at time step T and the latent representation the next time step given the current latent representation ZT. Finally, the same empowerment term integrated with the value function gives us an objective for planning, where it serves as an intrinsic reward signal in addition to the reward-based value term. This empowerment term in planning incentivizes choosing actions that can be predicted from consecutive latent states. So we are incentivizing the policy to choose actions such that those actions are predictable given successive latent representations. This completes the description of our approach InfoPower, where we have a representation learning phase on the left and a planning phase on the right. For experiments, we consider locomotion environments where an agent must be controlled with visual observations alone, and there are complex visual distractors that are playing in the background. And the research question that we ask is, how effective is our approach ignoring these visual distractors which are not relevant to the task, and ensuring that behaviors with similar latent states have similar latent abstractions? Here we show some visualizations of the learned model. As you can see, there are different videos playing in the background, but the agent in yellow in all the figures is performing the task without actually attending to the visual distractors. To compare against baselines, InfoPower in the solid line and in blue, we can see that it performs much better than the baselines in terms of episodic returns in the tasks from DeepMind Control Suite. In all these tasks, there are complex video distractors playing in the background. For the baselines, we have Dreamer, we have a contrastive version of Dreamer, we have an approach that tries to reconstruct the observations and the distractors separately, called Task-Informed Abstractions, TIA. We have deep biosimulation for control that learns the latent representation without reconstruction by enforcing a biosimulation metric in the learned latent space. And we have a deep MDP approach that is also similar to Dreamer. Ablation, we consider different variants of the mutual information contrastive term, namely the NWJ lower bound and NCE lower bound, and we consider variants of these InfoPower models without the empowerment objective in the policy learning phase. We see that when we don't include empowerment in policy learning, namely the last two variants, the performance drops significantly. And we see that the NWJ and the NCA lower bounds perform roughly equal in performance. Finally, we analyze the behavioral similarity of latent representations. For this, we consider DSNA plots of latent states and visualize three nearest neighbors for two randomly sampled points, which are shown in red frames. We see that the state of the agent is similar in each set for InfoPower. This suggests that the learned representations are such that the pose of the agent is prioritized and the background is ignored. Hence, we can see that the pose of the agent in all the nearest neighbors are roughly similar to red frame. And when we compare this to two of the baselines, we see that in the baselines, the poses of the agent are quite different. This suggests that the baselines are attending to the visual distractors more than our approach. In summary, we derived an approach for visual model-based reinforcement learning such that an agent can learn a latent state-space model and a policy by explicitly prioritizing the encoding of functionally relevant factors. Our prioritized objective integrates a term inspired by variational empowerment into a non-reconstruction objective for learning latent state-space models. Finally, through experiments on control environments with challenging visual distractors in the background, we show that compared to baselines, our approach achieves higher episodic rewards and better sample efficiency by ensuring that behaviorally similar latent states have similar representations. Thank you. Please check out our paper for more details.